And screen is visible.
Clear, ma'am. Clear, ma'am.
Okay. So let's start. So as we know, in real sense means in various disciplines, wide range of disciplines, data that are collected are multivariate in form. What does we mean by multivariate data? So we are going to collect the data on several random variables, and these several random variables will be on a number of units. Like unlike in univariate data where we find out the information only on a single random variable, but here we have several random variables on which we are recording the data. So what will happen? This will lead to a vector valued observation. Vector valued observation means we will be having number of units, several units, and several random variables on which the data is being collected. So as I have said, that majority of the data set which we find in practice are multivariate in nature. But if we are going to analyze the data in isolation, if we take only one variable and find out the relationship or any structure, then we may not be able to find the full structure of the data. And we are likely to miss some key features that is available in that data. So we go for a multivariate data analysis. So multivariate data analysis, here the data, as I said, is in the form of a matrix, vector valued or matrix. So as you can see, we have n units, okay, and we have q number of variables. So data structure will be in this form, where n is the number of units on which the data has been collected, and q variables are being recorded on each unit, and each values is represented by xij. Xij is the value of jth variable of ith unit, and the data structure will be in the form of a matrix, n by q matrix, which is in the contrast of univariate distribution, where we are finding out only on one random variable for n units. So next. So now I would like to say that we are going to work on data set in R for multivariate data analysis. The data is called as iris data set, which is available in R. So let me open my R, and I would like the participants also to open their R screen. Hope the screen is visible, the R Studio screen. Any response from the participants?
Yes, visible, madam.
Yeah.
Yes, ma'am. Yes, ma'am. Visible.
So I would request you all to please open your R screen. Okay. So we are going to work on this iris data set. So what is this iris data set? If you'll put question mark in front of this iris and run, then you can find on the right hand side window the description of the data. So what is this? This is the famous Fisher or Anderson iris data set, which has given the measurement of the variable. That variable name are sepal length, sepal width, petal length, and petal width of 50 flowers. So here the number n is 50, and the data has been taken for 3 species. Okay, so this is the description. So this is a sort of multivariate data where iris is a data frame with 150 cases, that is 150 rows and 5 variables. So here q is 5 and n is 150, because for each of the data, each of the species, we have 50 data. So 150 data set. So n is 150 and 5 variables. Okay, so this has been arranged in a form of multivariate. So this is a multivariate type of data. So when we are working in R, what we will do first, we will call the data set. So if you write data iris, okay, you write DATA, data in bracket iris. So this is going to read the data set iris. Okay, so after reading data, you would like to see the data set. So if we write iris and run, so you can see the whole data set. So what we would like to see, just the head, means just 6 rows of the data set. So we'll write head iris. This will give only first 6 rows. Similarly, if we would like to see the last 6 rows, we can write tail iris. This will give the last 6 rows. Okay. Now in statistics, if you would like to know the summary of the data set, then what we do, we write this summary, 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 and the name of the data. So the data set named is iris. So this gives us the summary of the data set. So what is it giving? About the sepal length, it is giving the minimum value, maximum value, first quadrant, median, mean, and also for the other variables as well, right? So this is just about the data set. Now I would like to switch to my presentation. Okay, so this was all about my data set. Okay, so covariances. What we know about covariance? Covariance is always is used to find out the weight between 2 random variables. Okay, it tells about the linear dependence among 2 random variables. But in multivariate data set, as I have already said, that we have q variables. So what happens if there are q variables? Then we are going to have q variances and the combination of 2 variables, that is total q into q minus 1 by 2 covariances. Sorry, it will be by 2 divided by 2. So what we find that these quantities are arranged in a q by q symmetric matrix, and the variance covariance matrix is denoted by sigma. The diagonal of this variance covariance matrix is the variances, and off diagonal, those except the diagonal values are their covariance, and these are mirror images. That means sigma 1 2 equals to sigma 2 1. Similarly, sigma 1 q equals to sigma q1, and the diagonal values, that sigma 1 square, sigma 2 square, are the variances. Now correlation, as we know, correlation coefficient gives us the measure of linear relationship between 2 variables. But when we have multivariate data, that is, we are having q variables, then there are q into q minus 2 distinct correlations. Similar to the case of covariances, as I have mentioned, we are also going to have this this matrix of correlation. Similar to the covariance matrix, this is also a q by q matrix. And in R, if we are going to find out the correlation, we'll use the function COR and the name of the data which you would like to find out the correlation. Now let's come to the principal component analysis. This is one of the important multivariate technique. So what is principal component analysis? It is a multivariate technique that aims to reduce the dimensionality of the data set while accounting for as much of the original variation as possible in the data set. So what we would like to infer is that if we are having a larger number of data, then we would like to reduce that number of variables into few variables. And this few variables still would be having the amount of original variation that was present in original data set that is still being captured. It's not being. So how is this? We are going to achieve this. For achieving this, we are going to transform the original set of variable into new set of uncorrelated variables that are the linear combination of the original variables. So the original variables are being transformed into new set of variables which are uncorrelated among themselves. And principal components, the first few principal components means first few combinations of the original data will be going to represent most of the variation in the original variable. So why we are going to do this? We would like to perform principal component because this will reduce the number of data set and we can use it for plotting the data, clustering or regression and many more techniques. It can also be viewed as a technique to remove multipolarity because when we transform the original data set, the data set gets uncorrelated. Okay. So let us let us assume that we have p variables. So first principal component will be defined as Z1 and it will be developed by using the same variables. So we will be having the same variables x1, x2, xp and the coefficients. Okay, the coefficients that is x11, x12 and so on are such that square of each of the coefficients added leads to 1. This is an important assumption, condition actually, which has to be fulfilled to get uncorrelated principal components. And the first principal component is going to capture as large as possible variability. So maximum variability will be captured by first principal component. Similarly, we'll be finding out the second principal component. Second principal component will be having variance. The variance of Z2 will be lesser than the Z1, but it will be greater than next Z's, this next principal components. So Z2 will be the combination of again the original variables and the coefficients will change. The coefficients is like A1, sorry, A21, A22, A2P. And the variance of this Z2 is as large as possible with respect to the next P principal component. Again, the condition that has to be fulfilled is that the square of the coefficients added is equal to 1. And also the covariance between Z1 and Z2 is 0 because we want the principal components to be uncorrelated. So this is an important condition that has to be fulfilled. Okay, and this coefficients is A11, A21, whatever, these are called the loadings of principal components. So once we have obtained the loadings, the value of age is A11, A22, and so on, the principal component, then we calculate the principal component score for each of the observation. So what would be the first principal component score? So it will be obtained by plugging the observed values of that observation into first linear combination. That is, if we are obtained the loadings and we already have the values of original that variable x1, x2, x3. So we will multiply by that loadings and add them all to get the first principal component. Similarly, it can be done for principal scores. To obtain and principal scores, we'll go on to find out using the loadings of principal components. So how we would determine that how many principal components one need to retain and how to interpret those principal components. So there is a plot called as series plot. The series plot helps us to decide how much principal component one should retain. This I will show in the R, but just to introduce, I would like to say that this plot, there is a sort of, you can say a slope kind of thing. When a slope drops dramatically, means there is a elbow. You will find that there is an elbow, and the point there is an elbow. That means addition of any more principal component would not be much fruitful. So up to that point, we are going to select the principal component. Mostly the principal component we select is up to 2 or 3 because it captures maximum of the variability about 80-85% in most of the cases. Another plot is that biplot. It is a very popular plot which is used for visualization of results from principal component. This is also said as an enhanced scatter plot because it combines both principal component scores and loading vector in a single plot. Okay, so this I will describe more when we do the practical. Here the points, in plot, whatever the points which we obtain represents the sample data. And there are two axes. One is for the principal component score, and another axis shows about the vectors and the vector loadings. So what does it help? Biplot helps us to it allows us to visualize how the sample relate to one another in a PCA. That means which sample are similar and which are different. It is revealed by this biplot, and how these variable contribute to the principal component. So how we are going to perform the principal component in R? So when we have variables in a form of a multivariate data set, the data set may be in different scale. Scale means it can be in different units or in different forms. So to perform PCA, what we will do first, we need to standardize those variables. So for standardizing those variables, we are going to use the function called scale function. So it's like subtracting by mean and dividing by standard deviation to make it uniform. Then PCA, the principal component analysis, is carried out using a function called PRCOMP. Okay. So this will be used to find out the principal component, and loading of each loading of PCA can be found out by the $ rotation. How it is done, I will explain in just now in R. And to obtain scree plot is using by using scree plot function, we will find get the scree plot, and we'll look at the elbow to find how much principal components to retain. Okay, so let's switch to R. Yes. So as I mentioned, the covariances. Yeah. So covariances we can use. We can obtain it by using VAR function iris. So what we'll do? We'll write VAR in bracket the name of the data set. Here the name is iris. If any another name you are having, XYZ or ABC, whatever, you can write that in the inside the bracket. So this the result when I ran this. This is the result. So what we find, the covariance matrix has been obtained, but the species it's showing NA because the species is in the form of the categories. Okay, so you can't find out the variance covariance matrix of that. So instead of that, we are going to use this function, covariance function. What we'll do, we'll write cov. This is the covariance function. iris data set, but we are going to now square bracket. What square bracket tells? Square bracket means number of rows and columns. So we are going to first, we are going to have all the rows and columns will be only for the sepal length, sepal width, petal length, and petal width. Okay, so only these columns will be selected, and we will have all the what we call the rows in the data set. So bracket close is for this C, and square bracket is for this matrix, where we are not writing anything before comma. That means we are going to select all the rows, bracket close. This will give the variance covariance matrix. So this is the matrix which we have obtained. The diagonals are the variances, and off diagonals are the covariances, right? Now, this is the variance covariance matrix for all the species. As I mentioned in the data set, we are having 3 species. What would, if you would like to know the variance covariance matrix species wise? So first, let us know how many species are there in the data set. So this data set, we would like to extract the values of only species. As you could recall, this the iris data set, the species, we had the 3 species. If we would like to extract only species values, only species name from iris data set, for extracting only one column, what we do, we use this dollar sign. So iris dollar species, this is going to give us the name of all the species that are available to us. So what we find, that we have 3 species: Setosa, versicolor, virginica. Now we are going to find, we would like to know the covariance, variance covariance matrix species wise, not all together. So what we use the covariance function to find out the covariance. Now we are going to work it on only on subset. How is the subset? The data set is named as iris, and species is equal to, see, we will write 2 times equal to. Species, in the species column, we are going to select only Setosa. Only Setosa will be selected, and it will be having for all the rows, and the column will be named only sepal length, sepal width, petal length, and petal width. Here we are not having any species. Already we are selecting only for Setosa species. So how it gives the result? So this will be the variance covariance matrix of only species Setosa, not for other 2. Okay, again the diagonal values are the variances, of diagonals are covariances, and you can see this value is equal to this value, right? Similarly, the off diagonals, this is equal to this value. So we did this for Setosa species. Again, this can be done for versicolor species. Similarly, what will change? We'll change the name of the species from Setosa to versicolor, right? And let's run this. We'll get another variance covariance matrix which will be only for versicolor species. Only those subset of data set which is related to species versicolor, not others, right? So I hope you are trying this along with me.
Yes, ma'am. Okay.
Okay. So this was all about variance covariance. Now, similarly, if you'd like to know the correlation. So for the finding correlation, we have the data set as iris, and we are having all the rows and column is sepal length, sepal width, petal length, and petal width. So this will give us this the correlation matrix. See, the diagonal is 1. Why? Because the correlation between sepal length and sepal length will be 1, obvious. Sepal width and sepal width will be 1. So the diagonal values are 1. This is the correlation matrix. And the value of diagonals, again, this value equals to this value. That is the correlation between sepal length and sepal width. Okay. Okay. Now, as I mentioned that if before going for principal component, we need to scale the values. For that, in R, we have function scale. So scale iris, and we are not considering here the species name because it is an what we say categorical variable. So we are going to select only the column sepal length, sepal width, petal length, petal width. Let's run this. So this gives us the scaled value for all 150 data set. Right? Now let's move to perform principal component analysis. In R, as I said, principal component is performed using PRCOMP. This is the function. And the data set, as I mentioned, is iris data set. And this square bracket, again, it denotes a matrix. So we are going to have all 150 data set. We are going to have all those rows and the column from 1 to 4. Why only 1 to 4? 1 double dot 4, 1 to 4, because fifth column is for species name. We are not going to find out any principal component using those categorical variables. And scale is true. Means we are going to scale the variable. So this will be calculating our principal component, and this value will be stored in a variable name called PC. You can name anything. I have mentioned PC. You can write any name, any this word or whatever of your choice. So let's run this. So this has run, and the value, the result has been stored in this variable name PC. So let's run PC. What's there? Let's see. So this is the PC, and this gives us the principal component. So it is giving us the standard deviation of this 1, 2, 3 up to 4 variables, and rotation. So what is rotation? The rotation is the loadings, the factor loadings. Okay, that means the loading of each PCs. As I mentioned, these are the coefficients of the new principal component that we created. As I mentioned, Z1 equals to A11 X1. This A11 and A2 plus A22 X2, and so on. So these are the values of rotation are the values of each coefficient of the new variable called as loadings. And as I mentioned, so if you would like to extract only rotation from this function PC, principal component, we'll write PC dollar rotation. It will give us only the rotation part of the our result. So see, this PC dollar rotation, it is giving only the factor loadings. So let's test how this principal component was performed. As you can recall that sum of the squares of all the loadings equal to 1. So let's sum all the factor loadings of first row, of first column, sorry. Means this A11 square plus A22 square plus A12 square plus A13 square plus A14 square should be equal to 1, as per the constraint which has been mentioned in principal component. Let's see whether it is being fulfilled or not. So let's run this. See, the sum of all the rotation equals to 1. So principal component, this is one important constraint, that the sum of all loadings should be equal to 1. Again, one more thing was that the correlation between first principal component and second principal component equals to 0. means the new set of variables, new set of principal component that has been generated are uncorrelated. So what we are going to find out, the correlation between, okay, so what is $X? So let's see what $X. See, $X, these are the principal component scores. What is principal component score? When we are going to multiply each of the principal component with each of the variables, then we are going to find out the PCS score, as I mentioned. So the two new this principal components are uncorrelated. So what we are going to see, the first principal component, so first column, see, the first column is principal component 1 and second column is principal component 2. First and second, these are going to be uncorrelated. So this has been written in the form of finding out the correlation between principal component $X. $X is giving this, extracting the score, and first column, first PC1. And this is showing the second PC. PC principal component, my variable name for principal component $X, we are going to extract the principal component scores PC2 and second column. These, the correlation between these two is, it should be 0. Okay, these are uncorrelated. Yeah, and round function is the rounding of the correlation. This correlation is getting rounded up to two digit. Round function is used in R to round the value. Otherwise, it will be showing in points and all. Fine. Now we'd like to see the principal component summary. What is the summary of the principal component, our PC variable name? So it is showing that we are having 4 principal components: PC1, PC2, PC3, PC4, right? And first row shows us the standard deviation of each of the PCs and proportion of variance that is being explained by these PCs. This principal component first is explaining 72.96% of the variation in the total data set. Total data, yeah. The second principal component is explaining 22.85% of the variation. And the cumulative variation by taking PC1 and PC2 comes to around 0.95, means 95.8% of the variation is being able to be explained by just first 2 principal components. So what we are going to do, we are going to select only first few, as I said. So since up to PC2 we are getting most of the variability is being captured. So 2, rather 3 also can be taken, because here we can see it is almost coming to 100%. 99.4% of the variation is being able to capture. So one method which is being used to decide that how much principal component is to be taken, as I mentioned, is using SRI plot. So SRI plot, the name of our variable is PC, and the type of plot where that will be developed in the form of lines. So let's run this line. See, this is the SRI plot, and the point that shows elbow means sudden drop is there. You can see it's at the point 3. So we can consider 3 principal components. Also, we can find that most of the variation is been explained by these 3 principal components. Right? Again, we have biplot. So the biplot PC is going to show us the biplot. So the biplot function is showing us the biplot of the variable. Now we'd like to have some better visual form of this principal component. So we are going to install one package called FACTO Extra. FACTO Extra. So the function is install.packages. This is going to install that package. I have already installed, so I'm not going to run this. So after the installation has been done of this package, we'll call the library of factor_extra. This also needs to have ggplot2. So it has been already loaded. So the function for performing this modified version of biplot, actually better version of biplot, is fviz pca underscore biplot. The variable name is pc, as I mentioned. Okay, so let's run. And the color that will be given will be on the basis of the different species that is available in our data set. So we have 3 species, so we'll having 3 colors used in this plot. So we obtain a PCA biplot using the that library, the package factor_extra, and the first principal component. See, dim1. It is the first principal component, which is as you can already see from the result of the summary PCA, that dimension 1, the first principal component is explaining about 73% of the variability, and second one is explaining about 22.9% of the variability. And we have obtained 3 colors. Setosa is in red, versicolor in a green, and virginica in a 3. Okay. So this is all about our principal component analysis. Let me switch to my slide. Next. Okay, so let's see how the biplot is being, it can be interpreted. Okay, so biplot we obtain. We find that many points are closer to each other. Okay, so these points that are closer to each other, each point is the value of the value of the observation. Okay, so those observations that have similar performance, similar type of performance, are closer to each other. Here we are talking about the species of the flower. Okay, so the flower that belong to the same species are located closer to each other. Here we can see in the biplot. See, all the flowers that have similar same species are located close to each other. That means they have similar principal scores. And the principal scores of the Setosa species is very low. Principal component 1 is very low for Setosa species. For versicolor, it is somewhat higher, and PC2 is also somewhat higher for versicolor. Similarly, for virginica, the PC1 score is relatively higher. Okay. Also, we can see the projection of principal component on PC1 axis. So what we find in PC1 axis, the petal length, sepal length. See the this is the petal length. Okay, petal length, sepal length, and petal width are same direction of PC1. Okay, so that means this 3 variables are positively correlated with PC1, and the sepal width is in opposite direction, means somewhat perpendicular to PC1, which implies that it has a negative association with the principal component 1. Now, another method which is being used.
Ma'am.
Yes.
Can you please explain that biplot again, ma'am?
Okay. So I have mentioned that each of these values, each of these observations, okay, these are the observations. Actually, it is too clumsy. It has become too close. These are the values of, these are the each observation. 150 observation has been mentioned as in the form of numbers. So it has come together. So the point that are closer, okay, they have similar scores. I mentioned that points, these are showing the scores, right? So the points that are closer to each other have similar principal competence scores and they have similar performances. And also we can see that the flowers means the species of the data set that are closer together. See, this species like Setosa, these all are coming closer to each other in a place, in a one place. So these have, that means these have a similar principal components.
Ma'am, your voice is not clear.
Ma'am, please unmute yourself.
One second, please.
Sorry, I got disconnected. I don't know how long I was disconnected.
No, ma'am, we are continuing. Last 2 or 3 minutes.
Okay.
You can share, ma'am.
Yes, yes. Okay, so visible and audible.
Yes, ma'am.
Hello. Yeah.
Ma'am, audible. Okay,
Okay.
continue.
Oh. Okay, so I was explaining the biplot. Somebody asked me to explain it again. We can see the projection of this sepal length, the petal length and petal width. So these arrows here, now these are somewhat parallel to PC1 in the direction of PC1. So we can say these three variables are positively correlated with principal component 1, whereas the sepal width, it is in opposite direction or somewhat perpendicular to PC1. So it has negative association with principal component 1. Okay. So let's move to cluster analysis. Can we take break of 5 minutes?
Ma'am, no problem. Okay.
Okay, let's take break for 5 minutes. Then I will start with this cluster analysis.
Okay, ma'am.
Okay.
So, dear candidate, tomorrow we have two classes. One will be on sampling technique from 11 to 1 and one in afternoon session 2:30 to 4:30. So tomorrow there will be two classes. So please prepare according the session. And many people message or mail us to send their Zoom link daily on basis because we have using same link daily. So you can connect to the same link daily basis. So no need to send again and again the same message to you.
So shall we start? Are we back from break?
Yes, ma'am. Continue, please.
So next method is cluster analysis. So the cluster analysis, why is it done? It is done to find natural or real groupings, if any, available in the data set. Okay. So cluster analysis, it is a primitive technique. It is said as primitive technique because it does not have any assumptions concerning to the number of groups to be taken. You can take any number of clusters, any number of group as per the choice. And this grouping is done on the basis of similarity or distance between the groups. So in the case of cluster analysis, the inputs are on the basis of similarity measures. And on the basis of that, we are going to find out how many clusters are there. So how many groupings of individuals can be made, right? So we are going to perform two types of cluster analysis. One is k-means clustering and hierarchical cluster analysis using R. So what is k-means clustering? So in k-means clustering, we are going to divide data into k groups or clusters. And this means pre-decided we are going to have that we are having k groups. And then we are going to assign each observation to the clusters that are closest, that are nearest. Those observations that are nearest are assigned to the clusters. And what is done in hierarchical clustering? We start with each unit as an entity. Okay, so there are n units, so n units will be there. Then we will merge two first units that are more similar, and they will become one entity. They will be put in one cluster. Then we will again examine the distance between remaining n-1 entities with that merged entity, and then merge that are more similar. This we are going to repeat it again until all the units are merged into one entity. So there are different methods to find out, measure the distance between two clusters. One is this is called a single distance, which is based on the nearest distance. Then complete method, which measured on the basis of farthest distance, then the average distance, centroid, etc. So let's perform this in R. Okay, so I'm going to take take the same data set of iris data set. First, we are going to scale the data. So I have named it as iris scaled. You can name it anything. And the scale function data set is iris. And we have all the rows taken, and the column will be only 4 selected: sepal length, sepal width, petal length, petal width. Okay, so this will give us the scaled value, and it will be stored in the variable name iris scaled. So iris scaled has the scaled value. So let's, if you would like to see the data, with right head iris scaled. So this is the scaled value of first 4, first 6 rows. Okay, now we are going to find out the k-mean clustering. And see, the data which we are going to have is the scaled, iris scaled, the variable name I have mentioned, iris scale. So this will be the name of the data. And 3 is the number of clusters which we would like to have. So here I would like to have 3 clusters. So I have mentioned it, iris scale 3, and the function for finding k-mean clustering is k-means. So k-means bracket the name of the function and number of the clusters we would like to have, and this is going to store I would like to store the value of this in variable name fit k. You can name it anything you want. So I named it as fit k. So let's run this. So what happens? This fit k we have obtained. So what is fit k? Let's run this. So it mentions the clusters. It is the fitting of the clusters. So the result is like this. It has performed k-mean clustering, where we have obtained 3 clusters, and each cluster is of size 47, 53, and 50. Okay, so these many clusters are there. And sorry, the mean of the clusters. So cluster mean for first the cluster, first cluster, the sepal length, the mean value is this. Similarly, the mean value of second cluster and so on. So this is giving the cluster means, and clustering vector means to which cluster the values are belonging. The first value belongs to third cluster, second is third cluster, and so on. 34th value is of third cluster. So it is mentioning that which of the observation is belonging to which cluster. The last observation is belonging to the second cluster. Then we obtain the within cluster sum of squares. Okay, so these are the results which is obtained by performing the cluster analysis using k-means function. Okay, so what is k-means? If you would like to know more about it, then what we'll do, we'll put question mark and k-means. So let's run this. We'll get more explanation about the what is k-means. K-means clustering. So the details has been given. So what is being done? The data is given by X are clustered by k-means clustering, which aims to partition the points into k groups. Here we have taken 3 groups, such that the sum of square from the point to assigned cluster center is minimized. At the minimum, all cluster centers are at the mean of the Voronoi set, and so on. So this algorithm was given by Hartigan and Wong in 1979, and so on. You can read the description, and if you would like to know more, you can know more about it. So this is k-mean clustering. Now let's see. We'd like to see the plot. Again, we are going to use fviz _ cluster. It is from Factor Extra, and we are going to plot the fit k, and data is iris scaled. So let's run this. Yeah, so this is the cluster plot. So we have obtained the cluster plot. Here you can see that distinctly we have 3 clusters. This is the cluster 1, cluster 2, and cluster 3. Right? So data has been plotted in the form of 3 clusters. K-mean clustering, we have assumed 3 clusters, and clearly we can see there are 3 clusters over here. Okay, Now let's perform hierarchical clustering. So it can be done using function hclust. 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 Let's see what's hclust and description. So I have written question mark hclust. Details has been given, how this has been performed, and so on. I've also discussed in the slide, so you can go for its description to know more about it. So before performing the cluster analysis using hierarchical method, first we would like to know the distance of the data set. Okay, so this is done by using the function dist, name of the, and in bracket name of the data set. So the variable name I have given as d, anything can be given. So let's define d as distance of iris scale. Okay, now we are going to fit hierarchical cluster. So hierarchical cluster is performed using function hclust, and variable d is taken, distance, and method complete. I have mentioned there are many methods. Here we are going to perform cluster analysis using complete linkage. So this hierarchical cluster has been stored in fitH. So let's run fitH to see what's that. fitH run. So it is showing that clustering method that has been used is complete. Distance has been calculated on the basis of Euclidean distance, and number of objects on which clustering has been performed is 150. Now it's like to see the dendrogram, the plot of this fitted cluster analysis. So plot fit H. This will provide the dendrogram of cluster analysis. So this is the dendrogram. Okay. So these are the each values. It's looking clumsy because it's come together. And the dendrogram has been developed on the basis of hierarchical cluster. Now we would like to cut the dendrogram tree, this dendrogram tree, into 3 clusters. So what we'll use? We'll use rect.hclust. This function is used to cut into 3, and border will be in the form of red. You can use any color name. I've used red. So the dendrogram will be cut into the 3 clusters using red line. See, so these are the 3 clusters in which our data, 150 data, has been divided, right? So this is about the cluster analysis.
Hello.
Next, yeah.
Ma'am, the distance you have mentioned here was Euclidean distance. Usually, like in our synopsis, we used to write like calculating distance using Mahalanobis distance. Is these both distances are same or?
No, distances are same. You can use that. The method will change the distance. You can mention which distance you would like to perform for clustering.
So Euclidean distance and Mahalanobis distance, these both are different.
Yes, it's different. You need to mention. See, when you are going to mention the method, no, in method you can mention the type of distance you want to use. Okay.
Okay, ma'am.
If you change the method and the variable name, see the members in hclust, how you can perform it is being shown over here. You can see the right side of my screen. I think I'm on R. No. Okay. When you give question mark hclust, you can see which type of distance you would like to know, which type of distance you can perform. So as per your requirement, you can change the type of method and get the result accordingly. Here I have taken complete. right?
Okay, ma'am.
Okay. Okay, so another method, another multivariate analysis method is factor analysis. So the factor analysis, the purpose of factor analysis is to describe the covariance relationship among many variables in terms of few underlying but unobservable random quantities called factors. This method is mostly used to uncover the relationship between the assumed latent variables. Variables that cannot be measured directly are called latent variables, and measurable variables. So here I have taken an example. Example is such that a manufacturing of fabricated parts is interested to identify the most successful salesperson. Okay, here he is having 7 variables, which he would like to reduce it to 2 or 3 factors, and would like to know how it is being done. So the data is such. I would like to share this data. Where I can share the data? Organizers, please help me.
Ma'am, you can
Chat
mail
में डालो।
to Kapil. This
अच्छा, ये
data,
chat
ma'am. Actually, ma'am,
ये-
after the session, we will provide them through email, ma'am.
Okay,
So-
okay. No, I would like the participants to perform some principal component जो मैंने बताया है. They would like now. ये बाद में ही share कर देंगे.
मैम बाद में शेयर करते हैं मैम सारे सेशन, वैसे भी
अच्छा।
रिकॉर्डेड सेशन सारे यूट्यूब पे हम डालेंगे, तो वहां से फिर
चलो।
ये वापस से प्रैक्टिस कर
हाँ।
सकते हैं जी।
Okay, okay, ठीक है.
आप कंटिन्यू किए मैम।
Okay, so this is the data set which I have of 14 salesperson, and we have 7 variables. These 7 variables we'd like to collapse into 3 factors. So the salesperson, we have the variables on height, weight, education, age, number of children, household size, and IQ. Now we'd like to reduce the 7 variables into 3 factors. So factor analysis we have one important term, rotate. है ना? So rotate is the fact means what we do, we rotate the factors. So we rotate the factors such that the factor loadings will be as close as possible to the desired structure. Okay, so there are 2 types of rotation methods which are used. One is orthogonal rotation and oblique rotation. What is orthogonal rotation? The factors after rotation, they get uncorrelated. Example is the one of the popular method of rotation is Parallax rotation, and another method is oblique. Oblique means the rotation after rotation, the factors get correlated. One of the example is Promax rotation. Okay, so if we have not the complete response, like I mentioned the data set, ऐसा कभी हो सकता है, sometimes it can happen that we don't have the complete response and we have only variance and covariance matrix or correlation matrix, then also still we can perform the factor analysis, and this will give the same result as of the original data set. Again, an important term that I used is factor loadings. So let's first do in the R, then I will explain this slide. Okay. So factor analysis is performed using function fact anal. Okay. So let's see what is fact anal. Question mark fact anal. So it is showing sorry, description of the factor analysis. How is it performed and what is it? So it is based on a model X is so and so. Here lambda is the loading, and k elements of F scores and p element, and so on. You can go into description of it. Okay. So fact analysis. So let's first read the data. As I mentioned that I have another data set of salesperson. So what I'm going to do, I'm going to read the file which is saved in the form of CSV, and file.choose headed true. So it will be read in the form of variable name fact. So this will be having the data set. So let's run this, and it will ask to browse. So I'm going to browse, and this is my data set. Okay, so I would like to see how the data set looks. So I would like to see only the first few six lines. I have done head fact. So this is the data set. Data set has been read into my R. Okay, the salesperson. It is giving the data on salesperson, height, weight, and all the variables that has been available. Okay. Now I'm going to perform factor analysis. So as I mentioned, it is done by function fact anal, and the data is fact. We would like to have 3 factors and rotation on the basis of Farimax rotation. Okay. So this will be saved in the variable name fit. So we like to see the results, what's there in fit. So let's run fit, FID fit. So this is the result. So what is saying? It is uniqueness. It's showing the uniqueness of the variable that is not shared variable, unique variable name, variable variance, sorry. Then factor loadings. We have asked for 3 factors, 1, 2, 3. So it is showing 3 factors, and we can see some blanks are there. Blanks means the value is very less, means approximately 0. So those values it is not showing. Those are the blanks. So this is the factor loadings, and the proportion of variance that is being explained by the factors. So first factor is going to show means the proportion of variance explained by the first factor is 37.6, second factor is 24.9, and third factor is something around 17.1. Cumulative variance that is being explained by the first 2 is around 62.5, and around 80% of the variance has been explained by all the 3 factors. So this is factor analysis. Since we have full data set, now let's assume that we have only covariance matrix. So I've taken one variable name cov.mat. It is going to have only the covariance matrix of the original data set. Okay, now let's see what result we obtain using this data set having only the covariance matrix, variance covariance matrix. So the function that we are going to use is factanal. The cov.mat, the matrix of covariance is cov.mat, which we have named the function name, and 3 factors are we are going to have, and number of observation is number of rows that is available in the original variable fact. So here we can find that we obtained a similar result. The result is same when we have the original data set, and instead of that, if you have only covariance matrix, the result is same. Okay, then we would like to know the scores, factor scores. So for that, what we are going to do, fact anal, x is equal to fact. Fact is our the data which we have mentioned. Factors 3 and scores. We are going to find out scores on the basis of regression. Okay. So let's run this and see the output dollar score. It will show only the scores. and we would like to see only the first 6 scores, so head function. So these are the output, the scores of the factors, right? Okay, so the factor loadings and the variance. So how we are going to discuss how we are going to interpret. So loadings, as I mentioned, which were shown as smaller than 0.1, which is very small, are shown as blank in the output. So need not worry when we are getting blank. And uniqueness is the variance that is unique to the variable and not shared with the other variable. The factor loadings depict the relative importance of each variable with respect to a particular factor. So here we can see, as we have seen in our data set, in our result, that in all the 3 factors, age and IQ have had positive loading. Okay, so what does it mean if you have positive loading? That means these are the variables of importance, which can be used in determining the success of the salesperson, because the main criteria, main question was to identify the successful salesperson, where 7 factors were there, and we would like to reduce into 7 variables were reduced into 3 factors. So here, as I have already explained, the factor 1 accounted for 37.6% of the total variance. Factor 2 was for 24.9%. Factor 3 was for 17.1%. So together, all the 3 factors explained about 79.5% of the variance. If you would like to capture more variance, what we'll do? We can increase the number of variance, number of factors to be taken. We assumed here only 3 factors. It can be increased to 4 and see how many variances, how much amount of variance is being captured. Then you can move to 5 and so on as per the requirement. And factor scores, in addition to the loading structure, when a person wants to know the factor score of each individual, then we go for finding out the scores. For example, what is exactly first score on factor 1, factor 2, we'd like to know. This can be answered using factor scores. And as I have mentioned, that fact annual function is used to perform factor analysis, and scores can be find out by using the regression. Scores is equal to regression. And each score, what is each score? Each score is the weighted sum of the factor score, when the weights are determined by the factor loadings. So the factor loadings are used as weights multiplied by the variable value to get the factor scores. This is all about multivariate analysis. So any question or?
1 minute go.
So now the session is open for discussion. If anyone have any doubts, you can ask to madam.
Wonderful.
Actually, I wanted साथ साथ में लोग उसको प्रैक्टिस भी करते हैं, मुझे नहीं लग रहा है वो उन्होंने बस सुन लिया है. They will practice maybe later on, क्योंकि जब तक प्रैक्टिस नहीं करेंगे doubts won't come. Dr. Vijay, you are muted.
एक्चुअली मैम टाइम सिर्फ 2 घंटे हमने रखा था ना, तो इनको मतलब फाइल प्रोवाइड करना, फिर उसको प्रैक्टिस करना, सभी अभी बिगिनर हैं तो थोड़ा सा कॉम्प्लिकेटेड होता है, इसलिए हमने सारे रिकॉर्डेड लेक्चर उनको प्रोवाइड करेंगे और जो भी कोडेड फाइल होंगे वो उनको प्रैक्टिस के लिए हम देंगे, तो ये लेक्चर से बाद में भी सुन के उसको प्रैक्टिस कर सकते हैं.
अगर अभी डाउट नहीं हो रहा है तो दे कैन Means contact me anytime. Let me share my this mail ID. Chat में मैं share कर देती हूँ.
Ma'am, how we make a heat map for correlation of different variables in
उसके
R?
लिए उसके लिए another function है, मैंने तो उसको अभी describe नहीं किया है. Heat map can be created. आपको एक package करना पड़ेगा, and accordingly you need to follow the steps. So you can explore more in Google. So how to perform many more methods and to generate different type of colorful and intuitive and very good maps.
I think Vijay, you include the making of heat map in R.
सर एक्चुअली हम बेसिक सिर्फ आर के देख रहे हैं, तो मतलब हीट मैप के लिए काफी सारे पैकेजेस हैं जो गूगल पे आप सर्च करोगे तो बहुत सारे पैकेज मिल जाएंगे, लेकिन बेसिक थिंग ये है कि हमें उनको यूज कैसे करना है, तो वो उसके लिए ट्रेनिंग का ये था. तो सर कोई ना, आपको हीट मैप के लिए जो भी कोड्स हैं वो हम प्रोवाइड कर देंगे.
हाँ, एक्चुअली हीट मैप से तो आपको कोरिलेशन ही पता चलेगा. जस्ट यू नीड टू यूज सम पैकेज एज पर योर रिक्वायरमेंट एंड द नीड, the point which you would like to explain. So basically it is going to show the correlation only.
Yes, for correlation, ma'am, for explaining the correlation of different variables.
Yeah.
Now many papers use heat map.
Yes, yes.
But it is already a function in our heat map, and it is under the package of, I think, ggplot, I think so.
ggplot,
So directly you can use it.
Okay, Kapil.
So finally, ma'am, we really appreciate the time and effort you put into preparing a detailed and helpful lecture on this multivariate analysis. And you showed us how to use R to data analysis for multivariates. So this session not only helped us understand the subject better, but also inspired us to learn more about it. So I'm thank you once again for sharing your knowledge and giving an excellent lecture. Thank you.
I thank the organizers, especially Kapil, for contacting me and requesting me for this lecture on good topic. So thank you the organizers for inviting me to deliver this lecture.
Thank you, ma'am. Okay.